We have a box of mass M that's on the ground, and we are going to pull the box along the ground with a force F. In this thought experiment, we are going to require that this force is constant, so the force of our pull is not going to change with time. It will not change the direction of the pull, or it will not change the strength of the pull. But we are going to allow this force to be directed at some angle theta above the horizontal. So if I draw a picture of this scenario, I have my box of mass M. This box initially is going to be located right here. So I'll say this is the initial position of the box. We pull on the box with some force F that is directed at an angle theta above the horizontal. And after some amount of time, we've pulled the box. The box is going to end up over here at some final position that I will call X final. Now, because the box itself has a very well-defined notion of initial position and final position, I could meaningfully talk about the box having undergone a displacement, because displacement is a change in position. So I have a well-defined notion of the displacement of the box. Displacement is a vector pointing from initial position to final position. And so displacement is your change in position. Now, because the force of our pull is the only force in the horizontal direction that we are considering for this particular thought experiment, the box will accelerate across the ground. In other words, we are assuming the surface is frictionless. So I could meaningfully talk about the acceleration of the box to be pointing to the right. Now, let's consider the three forces that are acting on the box. We have the force of gravity. Gravity is going to always be around. That pulls the box straight down towards the center of the earth. We have the normal force. The box is staying on the ground. It's not falling through the surface of the ground. The normal force always points perpendicular to the surface. So in this scenario, the normal force points vertically upward. Gravity pulls down, normal force pulls upward. The only force we are considering that has a horizontal component is the force of our pull right here. So I could break the force of our pull into its horizontal and vertical components. I have the horizontal component of this force. I could write that as F cosine theta. And I have a vertical component of the force of my pull. I could write that as F sine theta. If I look at this picture and I consider Newton's second law, we could write that out. F net equals ma. I notice a is only in the horizontal direction. So if I were to write Newton's second law in the horizontal direction, F net x equals max. The only force that actually contributes to this displacement, the only force that causes this acceleration, is the force of my pull. And not the entire force of my pull, the horizontal component of that force. So the only force that has a non-zero horizontal component is this force, and that is F cos theta. So I can write F cosine theta. The horizontal component of gravity is 0. The horizontal component of the normal force is 0. I don't feel like writing 0 plus F cos theta on the left-hand side here. On the right-hand side of Newton's second law, I could write that as equals to max. Now, just because we can, it may not be immediately obvious why we're doing this, but just because, let's multiply both sides of this equation by delta x, by the displacement that the box undergoes. So I could write this as F times cosine theta times delta x. And I could write that as equal to max delta x. It may, as I said, it may not be immediately obvious why we're doing this, but for the moment, we are allowed to do this. There's no reason that we can't do it. So let's now look at the right-hand side of Newton's second law here. I see an a and a delta x, and Let's think, where have we seen AX delta X before? And we think to chapter 2 when we learned about 1D motion, then chapter 3 we just generalized what we learned in chapter 2 to two directions. And we had this equation of Vx squared equals V initial x squared plus 2AX delta X. So if I wanted, I could take this equation and rearrange it, and I could write it as 1/2 Vx squared minus V initial x squared equals AX delta X. So I have AX delta X all by itself on one side, everything else is on the other side. I'm going to take this term and plug it in right here. So I could write this as F cosine theta delta X equals M times 1/2 Vx minus V initial x, and both of these terms are squared. Now, at this point, I'm not going to change anything I'm not going to do any algebra on this. I'm just going to rearrange the terms. So I could write this as F delta X cosine theta on the left side. On the right side, I'm going to write this as 1/2 times M Vx squared minus 1/2 M V initial x squared. So from going to this line, I did not actually change anything. I just rearranged the order of the terms. Now, what is delta x? Well, delta x is your displacement. So I'm just going to replace delta x with d, the displacement. So I can write this as f d cosine theta. Now, what is Vx squared? What is V naught x squared? Well, this is really final speed and initial speed. The box is only moving in the horizontal direction in this particular example. So I could say the full speed of the box with which it is moving is going to be just the x component of the velocity. So here, this is 1/2 times the mass of the box times the final speed of the box minus 1/2 times the mass of the box times the initial speed of the box. So I could just write this term then as 1/2 m v final squared minus 1/2 m v initial squared. I said at the very beginning of this example, the box will have an initial position. We pull on the box, and then the box has some final position. As a result of us pulling on the box accelerates. I did not really specify whether or not the box is initially moving. Maybe it was stationary, or maybe it was moving. I didn't tell you, but it turns out it doesn't really matter. If the box we assume to be stationary initially, then this V initial term would just be 0. But even if that's not the case, even if the box were moving, that would still be allowed. Let's now consider what we actually found. On the left-hand side of this equal sign, we have FD cosine theta. And we said in the previous video that work is defined as FD cosine theta. So this term here is the work done on the box by our force F. We also talked about in those videos, okay, we have an equation for work, but how could we visualize and gain intuition for what work is? And we said that you could imagine work as the energy given to an object when you push on that object or pull on it. When you apply a force to an object and that object moves, you will be giving energy to the object or taking energy away from it. And so I could think of the left-hand side of this equal sign as the energy given to the box. So let's think about what we are saying. This is the energy that we give to the box as a result of us pulling on the box. What would that implicitly mean? We have a box and that box is doing its thing. I could imagine that that box has some amount of energy associated with it. And then we come along, we pull on the box. As a result of us pulling on the box, we gave energy to the box. And after we're done pulling on the box, that box will have a different amount of energy associated with it. So we could meaningfully talk about the notion of an initial energy and a final energy. If I look at the right-hand side of this equal sign, throughout this thought experiment, the mass of the box never changed, but I still have a quantity where I have a notion of an initial value for that quantity and a final value for that quantity. That quantity on the right side of the equal sign that I'm talking about is 1/2 mv squared. It is this quantity that changes from the initial value to the final value. So I could imagine that the energy of the box is going to be described by 1/2 mv squared. This is the difference in these two quantities is the amount of energy I gave to the box. So we can now ask ourselves, is this quantity the kinetic energy, the energy affiliated with motion, or is this quantity potential energy, the energy affiliated with position? So I look at this equation and I do not see any term that describes the box's location. If there is nothing specifying the box's location, I could infer that this is not going to be the energy of position. I could look at this equation and ask, is there a term that describes the box's motion? And yes, there is. The speed of the box, that has something to do with motion. So this 1/2 mv squared is going to be the energy that is associated with motion. In other words, this will be kinetic energy. Now, in doing this, we said that the work done on the box by our force is going to be equal to the change in the box's kinetic energy. We have a notion of an initial kinetic energy, and we have a notion of a final kinetic energy. So throughout this thought experiment, we considered the force that is acting on the box as a result of our pull. Technically speaking, there is a force of gravity pulling the box down. There is the normal force pushing the box upward. But if you look at this picture, you could convince yourself that because gravity is perpendicular to displacement, because normal force is perpendicular to displacement, those forces will not contribute to the change in the box's speed. And as a result of this, I could generalize this statement to say the net work done on an object, the work done by all the forces, is going to result in a change in an object's kinetic energy, where kinetic energy is defined with this term here. So how do we actually find the net work done on an object? There are two ways we could think about that question. One thing we could do is we could say the net work done on an object, the work done on the object by all the forces, is going to be equal to the net force acting on the object times the displacement vector times the cosine of the angle between the direction of the displacement vector and the direction of the net force. So in other words, I could take all the forces that are acting on the object, I could add those forces as vectors, find the magnitude of the net force acting on the object, determine the direction of the net force acting on an object, and take the angle between the direction of that net force and direction of displacement, and then find W net this way. Another way we could find the net work on an object is to consider the sum of all the individual works done by all the different forces. So I could say the net work done on an object will be the work done on the object by gravity, plus the work done on the object by the normal force, plus the work done on the object by the force of our pull. And in this particular example that we considered, we said there were only 3 forces acting on an object, so there will only be 3 things that contribute to the work done on the object. But in general, if you have 4, 5, or 6 forces in some other scenario, you would need to consider the work done by all those other forces as well. So the work done by the force of our pull would be WF is equal to FD times the cosine of the angle between the direction of the force and the direction of the displacement vector. That is this angle theta here. Well, this is one term in the net work done on an object. But if I think about this, the force of gravity is going to pull straight down on the object. So here is the force of gravity. And the normal force is going to push on the object straight upward. So here is the normal force acting on the object. So I could say the work done by gravity will be the force of gravity times the displacement of the object through the distance through which the object moves. But the angle between the force of gravity and the displacement vector is 90 degrees. These two vectors are orthogonal to each other, so I would get cosine of 90 degrees, and cosine of 90 degrees is just 0. And similarly, the work done by the normal force will be the strength of the normal force itself times the displacement through which the box moves. But again, the displacement vector points entirely to the right. The normal force is entirely vertically upward. So the displacement vector is perpendicular to the normal force vector. So again, we have cosine of 90 degrees, and that will cause this entire term to just be 0 again. Now, hypothetically, if you want, you could consider this scenario where friction might also be involved. In this case, we would need to calculate the work done by friction and consider that when we are determining the net work. And in that case, friction will tend to also affect the final kinetic energy, how much energy net is given to the box. So in that scenario, I could imagine my force is giving energy to the box, but then friction is going to tax some amount of that energy. Friction will take away some of that energy that I give to the box. So in this scenario, we would need to consider all the works done by all the forces acting on the object, and then we would add them up to find the net work. Both of these methods are equally valid. They are both correct. So you could use either one. Sometimes one might be easier, sometimes the other might be easier. So as I said before, if you want as an exercise, you could consider this exact same scenario, but consider it in the case where there is also a force of friction that is tending to slow down the box or acting against the box's motion. But you will still end up with the exact same result, because at any given moment, the box could only have one speed associated with it. So we'll still have a notion of initial speed and final speed, and you'll still end up at this work kinetic energy theorem. The net work done on an object is equal to the object's change in kinetic energy, and we demonstrated through this thought experiment that kinetic energy could be written in this form.